I have here the free response question 5 from the 2012 AP Calculus BC exam. So we're going to solve all the parts in the next series of videos, and let's get right into it. Let's read it. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at time t days after it is first weighed, then the derivative of b with respect to t is 1/5 times 100 minus b. That's why the rate at which the baby bird gains weight is proportional to the difference between its adult weight and its current weight, is that 100 minus b. So y equals b of t. Let that be the solution to the differential equation above with the initial condition b of 0 equals 20. So part A asks, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. So let's think about this a little bit. The rate at which the bird is gaining weight, that is dB dt. So that's what we're looking at here. And the question is, when b equals 40, so b equals 40, is dB dt, is this going to be greater than when b equals 70 or less? So let's think about it. dB dt when b equals 40, this is going to equal 1/5 times 100 minus b. This is 100, b is 40, so minus 40. So this is equal to 60 divided by 5, which we could simplify, but it doesn't matter for the sake of the question. Now, if we look at if b equals 70, we get that the derivative of this bird's weight with respect to time at 70 equals 1/5 times 100 minus 70. Well, we're subtracting a bigger number, so intuition already tells us we're going to get a smaller dB dt, and indeed that's what we see. 60 divided by 5 is clearly greater than 30 divided by 5, and if we were to simplify, 60 divided by 5 is, 12? So 12 is greater than, this is 6 here, 12 is greater than 6, implies that the bird gains weight faster when it weighs 40 grams, when we're subtracting a smaller number from 100, when it weighs 40 grams. So this is the answer to part A, and that didn't take too long, so I think I'm going to go ahead and copy in part B of this too. See you in a second. Okay, so I copied in part B, and part B asks to find the second derivative of b with respect to time in terms of b. Use that second derivative to explain why the graph of b cannot resemble the following graph. So what they're trying to say here is when people see this 1/5 times 100 minus b, that might key them into think, okay, maybe this is logistic. And right here we do have a logistic function here. It starts at 20 and has that horizontal asymptote, and then it ends at 100. And the question is asking us to prove why this cannot be a logistic function. So with that out of the way, let's try to calculate it. We already know that the derivative of b with respect to t is this value right here, 1/5 times 100 minus b. How would we find the second derivative? Well, a good first place to start would be to expand this part out here, because we see we're going to have a constant that's going to go away. So let's do that. We get the derivative of b with respect to t is 1/5 times 100, that's 20, minus b divided by 5. Now that we have this, we can take an implicit derivative on both of these sides. So how do we do that? We'd say, okay, well, the derivative of b with respect to t, the derivative of that's what we're looking for, right? This is that second derivative of b with respect to t. This side is slightly more complicated. The 20 is simple. That goes to 0. But then b divided by 5. To do this, we have to remember that if we're trying to take the derivative with respect to t, b itself is a function of t. So we have this expression. This we can write, I'm going to get rid of the 0 here and take out the fifth. We can write this here as the derivative, right? It's just the derivative of b with respect to t. So this is db dt, and this is the second derivative. And at this point, normally in a problem, you might be stumped, because this is just a harder differential equation. You don't know what db dt is. But in this special case, the problem tells us what that first derivative is. So we can go ahead and substitute that in to get the second derivative, which is going to be negative 1/5 times positive 1/5 times 100 minus b. And that is going to give us our final answer of the second derivative of b with respect to t is negative 1/25 times 100 minus b. That is the first part of the question. Find the second derivative of b in terms of, find the second derivative of b with respect to t in terms of b. Now for the second part of this question, we have to explain why this proves that the graph of b cannot be this logistic function. So let's try our best to do that now. And what we have to notice here is concavity. If we split this graph here down the middle, we have two distinct parts of the graph. This graph that cannot be our actual graph. We have a part that almost looks like an upward parabola for this first part. It's going up, otherwise known as the concavity, or second derivative, is more than 0. This second part almost looks like a downwards parabola. The concavity here is less than 0. But that is not what we see with the second derivative that we just calculated, which we know has to be true. This second derivative we see has this. So if we're trying to figure out when this is more than 0 or greater than 0, what we can say is, well, first of all, the bird is never going to have a negative weight. So that gives us the constraint that the weight of the bird has to always be greater than 0. If the weight of the bird has to always be greater than 0, that tells us that 100 minus the weight of the bird is also going to be, well, we should take one step back. Not only do we know that the bird's weight is more than 0, we can analyze the original differential equation here, this db dt equals 1/5 times 100 minus b. We can analyze this, and what we can learn is that b also has to be less than 100. Think about this. If you think of an intuitive Euler's method, at every point, this 100 minus b term, it's getting scaled by the 1/5, but it doesn't really matter. This 100 minus b term is going to be how far away from 100 b is. If b was 0, this is going to be a really big number, so that first jump is going to be quite large. Now, if b was now maybe 20, now it's going to be still a large step, but slightly less steep. And as you go on, as you near 100, you're going to be making a horizontal asymptote. Think if b was 99. db dt would be 1/5 times, well, 100 minus 99 is 1. If it was 99.999, then db dt is going to be even smaller. So for larger b's, for b's closer to 100, db dt will approach 0. It'll go to 0. So, because of that, there's going to be a horizontal asymptote at b equals 100. Therefore, b can never exceed 100. So if b is always greater than 0 and less than 100, that tells us that 100 minus b, just returning to our train of thought here, 100 minus b, this here has to be greater than 0. It's going to be a positive number. And because this is always a positive number, negative 25th here is going to be multiplying into it, you know that the second derivative of b with respect to time, this is always going to be less than 0. you're always going to be almost like an upside down parabola. You're always curving down. And because of that, you know it cannot look like this graph. Because clearly, this graph has a part where the concavity is less than 0. But similarly, it has a part where the concavity is greater than 0. So we can write as our explanation for why the graph of B cannot resemble this graph here, that the graph presented has concavity greater than 0. Concavity greater than 0. Yet, or however, the second derivative of b with respect to time, this value that we just found, I should write my squares there, is always less than 0. And this is a proof, because if there's ever an inconsistency here, we've proved that it cannot be. So that is part B of this question. I think in the next video, we're going to tackle part C.